Hello again. This is Math 2232 coming to you from the College of DuPage, and the title of this lecture is 3 Very Special Types of Series. As always, be attentive while watching this video. By way of introduction, in this section we're going to take a brief look at 3 special series. And special might not really be the correct term, but all 3 have names, which makes them special in some way. But we're looking at them because 2 of them will allow us to sum series, which is actually kind of an amazing thing. We'll get actual values for this series. The third type is a divergent series, and so we won't have a value to worry about, but it's a very, very, very important series. So in general, determining the value of a series is very difficult, and outside of these special series, we will not be determining the values very much in this chapter and in this course. The first of these is called a geometric series. A geometric series is any series that can be written in the form summation I from n equal 1 to infinity of a, that's a constant, times r, which is one of your parameters, raised to the n minus 1. Or if we do a shift index, the geometric series could be written as summation from n equals 0 to infinity, or actually you could go from any lower level, and this is a times r to the n in this case. Now these 2 things, as you know from our discussions of the shifts, are identical series and they have identical values provided they converge, of course. Let's do some analysis and derive a formula. So if we start with the first form, which is this one, what we find is that Sn, the partial sums, can be a times 1 minus r to the n, all divided by 1 minus r. And if I distribute and get these over common denominator, or split these into 2 fractions, I can have a over r 1 minus r and a times r to the n over 1 minus r. And by the way, the derivation of this formula is actually pretty easy. So we start with Sn here being the sum, so that is a, and as ar is ar squared, ar cubed, and so on and so forth. So I'm really just expanding this first one up here. But then if I multiply all the way through by r, I get this. And you see many of these, and I deliberately wrote these on top of each other because I'm going to subtract the bottom equation here from the top. And most things will cancel out. When you subtract, these will all cancel out, and you'll be left with Sn minus Rsn is equal to, we have the a left, and then this is minus a r to the n. So I can factor the Sn out of here. So as Sn times 1 minus r, and that's a 1 minus r, and then I solve by dividing all the way through by 1 minus r. I can do that if r is not equal to 1, and I get this formula, which is the same as this formula. Okay, so what will happen is this series will converge provided the partial sums form a convergent sequence. So let's look at the limit of these partial sums then. Well, so this limit as n goes to infinity of Sn is a limit as n goes to infinity of this business. This has no n in it, so that is just a constant. And here, the only thing that has an n in it is that r to the n, so I can factor it out. So make sure you follow the algebra, but we did that calculation. So I have a over 1 minus r, but then what happens is if r is between minus 1 and it cannot be equal to 1. This really should say less than as well. And that's, I guess, what they're saying here. So if r is between minus 1 and 1, another way to say that is the absolute value of r is less than 1, then the limit as r goes to infinity of r to the n gets smaller. For example, if it were 1/2, I'd say 1/2, and then the r n being 2 would be 1/4 and 1/8 and 1 16th, and so on and so forth. So that would go to 0. So all of this goes to 0. So at the end of the day, the formula is that the sum from n equal 1 to infinity of a r n minus 1, and I could write it shifted like this, but it's going to be a, the first term, divided by 1 minus r, where r is the multiplier. And you see each term in a geometric series, geometric sequence, is formed by multiplying by an r, which is called the ratio. That's why they use r for that. Okay, so note in this formula, we need to make sure that we are in the correct form. In other words, if the series starts at n equals 0, then the exponent on the r must be n. Likewise, if the series starts at n equal 1, then the exponent on the r must be n minus 1, and so on. And in fact, more generally, you do have to be mindful of where the series starts. But now we have a formula that you want to commit to memory, and we can use to solve problems. And let's use it to solve this problem. So I'm asking you to determine if the following series, there's two, A and B, converge or diverge. If they converge, give the value of the series. If they diverge, you should explain why. You know what to do. Let's see how you did. Okay, well, basically, this is what we started with. And the idea is we would like to morph this into a geometric series, which can be done. So first thing I'm going to do is note that minus n plus 2 is the same thing as minus the whole of n minus 2. And then I got 4, so this is going to be 4 to the n plus 1 over, and this 9 to the n minus 2 is in the denominator. Now these exponents don't match, so I have to force them to match. So what I'm going to do is I'm going to note that 4 to the n plus 1 is the same thing as 4 to the n minus 1 times 4 squared. And 9 to the n minus 2 is the same thing as 9 to the n minus 1 minus 1. So you see 16 over 1 over 9 can be factored out. Or I can write them this way, but now I have 4 to the n minus 1 over 9 to the n minus 1. Now 16 times 9 is 144. And so you see now I have this in the form of a geometric series. A is 144, R is less than 1, it is 409, and since the absolute value of R is less than 1, I can use my formula. I use it down here and do the arithmetic, and you should follow the arithmetic, but I get this is 1296 over 5. Some of my students would think that is an ugly number, but there are no ugly numbers, just like there are no ugly babies. Okay, here's the second problem. And the second problem, when we, oh, excuse me, that was the first problem, and we got this 1296 over 5. I think I'm repeating myself. Here's the second problem, though, and we have this. Now, again, you're kind of thinking, oh, this is probably a geometric series, but I need to make it into a geometric series. So I do some gymnastics with this. And you can see playing games with the exponents. But at the end of those gymnastics, I get that this is going to be the summation n equals 0 to infinity of 5 times, and this n that we have here is minus 64 over 5n. Now, the absolute value of that r is bigger than 1, so we know from the theory that this series diverges. Now, previously we talked about stripping out terms, and here's a couple of examples, and notice that these start different places. Here we start at n equals 0, and here we start at n equal 3, but we're talking about using the results from the earlier example to determine the value. You know what to do. Let's see how you did. Okay, so on this one, we strip out the first term, which is this, and now we're summing from n equal 1. And we have this, which is what we were talking about in the first problem. And so what we're going to have is this, when we multiply 81 times 4, we get 324 plus this. So this is 324 plus, we learned this in the previous problem, this was 1296 over 5. And so when you add those two things, getting a common denominator, you get 2916 over 5. Part B starts out looking like this, but this time I have to strip out two terms to make it look like what we had before. And so this is going to be, this is when n equal 1, this is when n equal 2. And so then we have the remainder at n equal 3. So these add up to, if you do the arithmetic, 2008. And then we had the sum from n equal 3 to this. Now what we can do is we can do a shifting, as we talked about before. So the summation n equal 3 to infinity of 9 to the minus n plus 2, 4 to the n minus 1 is the same thing as I can do shifting, and I can get what we have up here. And so I will end up, when I shift this, I will get, this is 1296 over 5 minus 2008. And so this is going to be 256 over 5. Make sure you follow these calculations. Notice that we didn't discuss the convergence of either of the series in the above example because, and here's why. We consider the series written in two separate ways if we strip out some terms. If we know that the one of the series is convergent, then one that has a finite bunch of extra terms has to be convergent because that's just a finite number. Also, likewise, suppose that it's convergent. If we subtract off three finite numbers from this, it still is finite, so it is also convergent. In other words, the takeaway is if we have two series and they differ by only the presence or absence of a finite number of terms, they will both either be convergent or they both will be divergent. The difference of few terms one way or the other will not change the convergence of a series. This is an important idea, and we will use it several times in the following to simplify some of the tests that we will be looking at. It's all in the tail. The first finite number of terms do not matter as far as the convergence or divergence. It's all about the tail. This is a picture that I cut out of a Walmart ad for a collapsing telescope. And that is our introduction to talking about telescoping series, which is the second of the three very special series. So now we're going to look at the second, and the name comes, you'll see where the name comes from as we go through. Okay, and again, I put this mark here because these are good problems for you to practice. Okay, so here's what the problem says. Determine if the following series converges or diverges. If it converges, finds its value, and this is the summation from n equals 0 to infinity of 1 over, this is n squared plus 3n plus 2. So what we want to do is we want to look at the partial sums. So we go from I equals 0 to n with this, and those are the partial sums. And again, that's a dummy variable, so I can change it that way. But now what we're going to do is we're going to look at this term in the summand, and we're going to realize that I can use partial fractions on that. And of course you can do Heaviside, and if I do partial fractions on that, which happens here, 1 over I squared plus 3I plus 2 factors into 1 over I plus 2 times I plus 1, and you can use Heaviside to call this 1 over I minus 1 minus 1 over I plus 2. Now you can check that partial fractioning and using Heaviside is good, and you should be good at this now because we've been doing this for a long time. Okay, but how did that help us? Well, let's see. So I can replace this by its partial fraction decomposition, certainly, and then I'm going to write out the terms and see what happens. So what happens when I is equal to 0? Well, when I equal to 0, it is 1 over 1 minus 1/2. What happens when I is equal to 1? It is 1/2 minus 1/3. When I is 2 is 1/3 minus 1/4 plus dot, 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 dot. But you see what happens is the minus half cancels with the plus 1/2. The minus 1/3 cancels with the plus, and so on and so forth. So everything cancels out. That's why you call it telescoping. So we just have the first and the last, which is n plus 2. Now, as n goes to infinity, we see that these partial sums go to 1. So that means the sequence of partial sums is convergent. And so the series is convergent and it has a value of 1. Now, in telescoping series, you want to be careful not to assume that just successive terms will be the one that cancels. Sometimes it's more complicated. And you'll see that in example 4. Here, you are to determine if the following series converges or diverges. If it converges, find its value. So this is the summation from n equal, I think that's 1 to infinity, 1 over n squared plus 4n plus 3. You know what to do. Let's see how you did. Okay, now again, we're going to do the heavy side and partial fraction decomposition. Again, you should know how to do this well. And we get this, and I can pull the 1/2 out in front, and I have this. But now notice what happens, and so the 1/2 is in front. But notice now that the terms don't cancel immediately. I get 1/2 minus 1/4, 1/3 minus 1/5. But this is where the plus 1/4, it will cancel with that, and this is minus 1/6, and so on, and it goes through. So you see, it's a more complicated expression that I get this time. This is 1/2 times 1/2 plus 1/3 minus 1 over n plus 2 minus 1 over n plus 3. So now, but we still are going to take the limit as n goes to infinity. And so this guy is going to go to 0, this guy is going to go to 0, and these numbers will add to 5 over 6. So this series up here sums to 5 over 12. And that's the answer. Note that it's not always obvious if a series is telescoping or not until you try to get the partial sums and actually check to see that things are telescoping. And there's no test to tell us if we got a telescoping series right off the bat. And in fact, you might say, well, anytime I can do partial fractions, that's true. No, that's not a test, because here you can do partial fractions on this series and this expression and get this. But notice this is not going to collapse. It's not going to be telescoping because the SIG in the middle is positive. So both of those are positive. Nothing is going to cancel out. And next we're going to address an issue that we raised in an earlier lecture. We stated the sum or difference of convergent series is also convergent, and the presence of a multiplicative constant would not affect the convergence of a series. Think about those. We've said them before, but we've said them now again. So let's do some examples of that. So here's example 5. Again, this is a good example for you to make sure that you understand, maybe even practice when you're studying for the final exam. But here we're to determine the value of the series, which is the summation n equal 1 of 4 over n squared plus 4n plus 3 minus 9 to the minus n plus 2, 4 to the n plus 1. Well, these are series we've seen before, so we're going to write this series as those two series. I'm going to jerk the 4 out, and then this is the series we studied before and got 5 over 12, and this is the story that we got, series that we got 1296 over 5. So we do all the calculations. Let's see, 4 will go into 12 3 times. That gives you a 15 as a common denominator, and you get that this series sums to a negative 3863 over 15. And we didn't discuss the convergence of the series because it's the sum of two convergent series, and that guaranteed the original series would also be convergent. The third and final series that we're going to talk about is one I already talked about in an earlier lecture. We'll just go through it, but we've talked about this. It's called the harmonic series. It's a summation from n equal 1 to infinity 1 over n. And I told you some things about this was music and things like that was where this came from. Now, we saw earlier, and in fact I proved to you using the French monk's proof that the harmonic series is divergent. And here it says we need to show this in the next section. I already showed you that. In fact, I showed you a proof that's going to be different than what we will see in the next section. But anyway, here's what we're supposed to do and how we're going to use it. So each of the following are, and I say divergent. Well, and again, this is something you want to understand. Well, this is going to be divergent because you can jerk the 5 out, and then this one diverges, so 5 times it diverges. And this is the tail of the harmonic series. It's all about the tail, so both of these diverge because you can discuss them readily in terms of the harmonic series. Let's look at ways to say that. Here we're jerking out the 5, but then we know that this one is divergent, so 5 times something divergent is divergent. And down here you can strip out the first couple of terms. In fact, you could have stripped out a whole bunch of terms, but this is going to be the tail, and the tail has to diverge, or else the whole thing wouldn't diverge. And so you conclude that those are divergent. And adding or subtracting a finite number from a divergent series doesn't change whether it diverges or not. Okay, so some general rules about convergent and divergent series should be stated. Multiply a series by a constant will not change the convergence or divergence, and adding or subtracting a constant from a series will not change the convergence or divergence. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.